Hello students, today we are going to discuss about Introduction to Solid Solution. This is the first part or part 1 of the fourth module. I am Sudipto Nath, your teacher, and you are with Materials Engineering. So regarding the introduction, you must understand that is the objective of engineering metallurgy is to determine the properties of material. And over here, two major variables are pressure and temperature. And thus it is to determine the phase present in the material system. An equilibrium or phase diagram is plotted. Equilibrium diagram or phase diagram, it is a graphical representation of various phases present in a material system at various temperature and composition point. Now uses of equilibrium or phase diagram are listed below. Shows the various phases present in different composition and temperature. It indicates solid solubility of one element in another. It shows the temperature range over which the solidification or liquidification of material system occurs. And the last one, it is very important that it indicates the temperature at which different phases start to melt. Now, whenever we are going to discuss about the phase diagram, some basic terms will appear which we must know. The number one is system. What is system? System is the substance or substances that isolated and unaffected by their surroundings. It may be composition of solid, liquid, gases or the combinations, and may have metals and non-metals separately or in any combination of them all. A system is capable of changing its composition, temperature, pressure, density, etc. So next thing comes in our mind is what is a phase? It is physically and chemical composition of a substance or system separated from the other portion by a surface and an interface. Each portion have different composition and properties. In equilibrium diagram, liquid is one phase and solid solution is another phase. The third one is variables. A particular phase exists under various conditions of pressure and temperature and composition. These parameters are known as variables or phases. As well as next come component. These are the substances, element or chemical compound whose presence is necessary and sufficient to make a system. A pure metal is one component system, whereas the alloy or metal of two component, that is binary component system, etc. Now when we are discussing about alloy, so obviously it is a mixture of two or more elements having metallic properties, and in this mixture metal is in the large portion and the other can be metal or non-metal. So obviously the next thing comes in our mind is Gibbs phase rule. Okay, so in the screen you can see that the phase rule formula is given, that is P plus F equal to C plus 2, where the number of variables are determined by P. F is the number of variables that can be changed independently without affecting the number of phases. C is the number of elements, and 2, it represents any two variables amongst temperature, pressure and composition. In general, all equilibrium diagram studies at constant pressure, it is done generally in constant pressure. So the Gibbs phase rule is modified to P plus F equal to C plus 1. We are considering, instead of taking 2, that is the independent variables, instead of taking 2 like pressure, temperature, we are only considering the variable as temperature. So it is a single phase criteria we are considering. Now this phase rule helps to determine the maximum number of phases present in an alloy system under equilibrium conditions at any point in the phase diagram. The phase rule can also be used to determine the degree of freedom which can be changed or altered. Now let us discuss about the solid solution and compound. Solid solution, it is a new term because whenever we are thinking of a solution, something liquid comes in our mind. But when we are discussing about solid solution, what does it mean? It means that a component or a phase, whenever it is mixed with another component or a phase at an elevated temperature homogeneously and then cooled down to the normal room temperature, if it is stable or if they are stable, then we call it a solid solution. There is a thin red line between the solid solution and the compound. Okay, let's check. The element present in the alloy in the large portion is referred as base metal or parent metal or solvent, and the other elements are referred as alloying element or solute. Solid solution is a type of alloy in which the atoms of alloying element are distributed in the base metal and both having similar crystal structure. The composition of alloying element may vary, but the structure should be similar to the base metal. So here is a chart that you can see that how the solid solutions are distinguished, like substitutional solid solution and interstitial solid solution. Substitutional solid solution, it is further, it is subdivided into two categories like regular or ordered type and random or disordered type. So let us check about substitutional solid solution. The name itself, it is telling that substitution, that is, it is substituting something or somebody. So the atoms of alloying element occupy the atomic size of the base metal. They are further classified as regular or ordered substitutional solid solution and irregular or discrete type solid solution. So let us check first the regular or ordered type, and after that we will check the disordered type solid solution. Now in this type, the solid substitutions of atoms of alloying element is in definite order in the base metal matrix. The examples are nickel aluminum solid solution, which occurs below 400 degrees centigrade. There is an image that you can see, that is in case of ordered substitutional solid solution, the nickel, which is the solvent, and aluminum is the solute, they are homogeneously distributed over here. So now random or disordered type substitutional solid solution. In this type, the substitution of alloying elements is in the random or disordered type within the base metal matrix. The examples are alpha brass. So over here you can see that is the copper, which is the solvent over here, and zinc is the solute over there. They are not mixed to one another in a very homogeneous manner. They are randomly distributed, that is zinc solute is randomly distributed over the copper solvent matrix. And then the other one, that is the interstitial solid solution. Interstitial solid solution means in case of the atoms of alloying elements, they are of different types. One is very large, the other one is very small. There is disparity among themselves. Then the interstitial sites of the base metal are generated. Now this type of solid solution is formed when the atomic size are much smaller compared to that of the base metal, like iron carbon system. In case of iron carbon system, the iron is very large and the carbon atoms are very small. So within the small space or gap between two adjacent or four adjacent or multiple adjacent iron atoms, a carbon atom can manage itself within that matrix. So it is called interstitial solid solution. Well, now it is very important, that is the Hume-Rothery's rule for solid solubility. So over here, the solid solution, we know it is an alloy of two or more elements wherein the atomic crystal structure of alloying elements or solute is the same as that of the base metal matrix or solvent. Now the solubility limit of the solute in the solvent of the alloying element in the base metal matrix is governed by certain factors. These governing factors are known as Hume-Rothery's rule for solid solubility. So let us check about the governing factors. First one is atomic size. Alloying elements having smaller atomic size as that of the base metal matrix have better solubility. For favorable solid solution formation, the difference of atomic size of solute and solvent should be less than 15%. Second criteria of Hume-Rothery's rule is chemical affinity. Elements having lower chemical affinity have greater solid solubility. Elements having higher chemical affinity have the tendency of formation of compound and hence restrict formation of solid solution. In general, the alloying element located closer in the periodic table have higher solid solubility because they are not much difference. They are having not much difference in their electronegativity value. Next is relative valency. Metals having lower valency have more solubility for metals having higher valency. I repeat, metals having lower valency have more solubility for metals having higher valency. Hence, for better solubility, the base metal selected should be one that has lower valency as compared to that of alloying elements. And the fourth part of the Hume-Rothery's rule is crystalline structure or crystal structure. As mentioned earlier, solid solution is an alloy of element having similar crystal structure. So the difference in crystal structure limits the solid solubility of the element. If you are having, you can mail me at this particular address given here. So this is the end of part 1 of module 4. Goodbye for today.